So welcome to the EC Game Changers online seminar. The seminar is how mission changed our view. The first part of our Game Changers seminars was on the solar system, and then in the universe. We were presenting starting from the early universe with Planck, then the cold universe with Herschel, then the extreme universe from the soft to hard X-ray spectroscopy, which was XMM Newton and integral. We were dealing also then with the deep Hubble Space Telescope images and with the Gaia, the dynamic mapping, the dynamical 3D sky, to also the first transit exoplanet mission Korot. And today, happy to, we cannot miss the Rossi X-ray Timing Explorer. I mean, Rossi X-ray Timing Explorer was in X-ray and in timing domain a game changer. And Tomaso apparently he was not only a game changer in science, but also a game changer in a lot of careers among us as a mission. And I am your host today. My name is Maurizio Falanga, working at the International Space Science Institute. And you are all welcome to visit the webpage of our institute to learn more about us. It's an institute who serves the space science community to come actually to EC and do science. So all the program we have, it's also the program that the community is submitting to EC. We have also the call for international teams. Deadline is in 7 days, but you're always also welcome to submit a team proposal in the future with your own teams and be founded by EC to come and work to EC. About Tomaso Belloni is research executive at ENAF, Brera Astronomical Observatory in Merate, Italy, and visiting professor at the University of Southampton, UK. Then his main research interests are in fast time variability from X-ray binaries, in particular black hole binaries, and the search for gravitational effects through timing analysis. So I would say Tomaso, it's a timing astronomer, and he worked with the RXTE data since its launch, and continues even today with the exploitation of its database, being also involved in the current Indian X-ray satellite AstroSat, and the planning of future missions like HEXTE. And he's of course also a member of several international committees like COSPAR, or also national committees as the science advisor panel of ENAF. At the end, all the participants or the attendees have the possibility to ask questions at the end. You have two possibilities to do this: or you raise your hand electronically, or you just write your questions in the chat. And the seminar will be recorded, and you can find this also starting from tomorrow online on our EC YouTube channel. Tomaso, normally I would say the floor is yours, but in this case I have to say the screen, or the screen is yours.
Thank you. Let me start the sharing. Does it show right?
Yes, it's okay. Fine with me.
So, okay, thank you very much, Maurizio, for inviting me to give this presentation. I have to say I was not part of the HEXTE mission in any way. I've just been a very, very prolific user of the data. But let's go into the description of why this satellite was really a game changer for our field, and starting, of course, with describing the mission itself. The Rossi X-ray Timing Explorer was launched at the end of 1995 in a very thrilling series of attempted launches, one of which went very close to complete disaster, 1 second to complete disaster. And then it finally was launched successfully. Its mission has been controlled at Goddard Space Flight Center at NASA, and the project scientist was Gene Swank, and then at the end replaced by Todd Strohmeyer. Nothing special about the orbit. It was a low Earth orbit, 23-degree inclination, about 90-minute period. And then you see here the launch and the picture of Bruno Rossi, who is the physicist that gave the name to the mission after launch. What is very important is that this was a very flexible satellite, and it could access most of the sky. In my field, things happen very rapidly. You have new transients in the sky. You try to trigger your satellites, and they usually tell you it's not observable anymore, or it's not yet observable, because there are very stringent criteria for observing, like position of the sun or things like that. And XTE was very flexible, could be used very flexibly, and it could observe large parts of the sky every single day. And it was optimized for timing studies. There were 3 instruments on board. Here you see a picture of the instrument of the satellite before launch. The proportional counter array was the big one, the PCA. It was built at NASA, at Goddard. Then there was the high energy X-ray timing experiment, HEXTE, built at UCSD, at the bottom in the picture. And then sticking out of the top in the picture, at the top, of course, was the All-Sky Monitor developed at MIT. And these 3 instruments worked very well together, as expected. The All-Sky Monitor was a set of 3 proportional counters, 3 cameras that were scanning the sky and with coded masks, and covering 80% of the sky every orbit. Now we have MAXI on the space station. We have BAT on Swift that scanned the whole sky. Then we only had this one, and it worked fantastically, very, very efficiently for the whole lifetime of 16 years of XTE. And it's, of course, essential to catch transient variability. You see here 2 sources over a long span of time, a non-transient but very variable source, GRS 1915, that we'll see later, and a transient neutron star Aquila X1. And this is these are light curves of 1 point per day made with the All-Sky Monitor. Then we had the proportional counter array, the big instrument. It was 5 big proportional counters with an energy range 2 to 60 keV. It was not making any image. It had collimators to restrict the field of view to 1 degree. Very good time resolution, a very large area, 6,500 square centimeters. I don't remember which energy. It had no independent background observations. It was just pointing at the source, and the background was calculated using some very, very precise model that always gave very good results. And then you had the high energy X-ray timing experiment, 2 clusters of 4 phosphate detectors to cover above 10 keV, up to formally 250 keV. And it was 2 clusters rocking on and off source to give the background information. Now this opened a very different window on the galaxy. If it runs, this is a movie of the All-Sky Monitor, which unfortunately is exceedingly long. So I'm going to show you the movie when it starts. Like here, you can see the time going on the upper right, and you can see the full sky, how it varies. On the left, now you see the sun that's moving in quotes, and that's moved to the right. And then you see different sources become different sizes depending on how strong they are. And then you see different events that happen during the lifetime of the satellite. It's quite a nice image that shows the dramatic X-ray sky. You see Cygnus X1 back to the hard state. It was red, meaning soft, and now it became yellow again, which is hard, and so on. And then you go on for 16 years of this of this movie that gave us a lot of data. It also gave us a different window to the galaxy, because this is an example of what we had, the best we had before RXTE. It is a light curve of a black hole transient made with the Japanese satellite Ginga. And it doesn't matter what's plotted there, it's flux versus time. And you can see each point, each little triangle or each circle, it's the same data, is one observation. And I worked on this data, and I was excited to have so many observations covering this period of 200 days. Now in 2005, RXTE observed one of these transients, and you see what it did here. This is not an All-Sky Monitor light curve. This is pointings. The bottom is hardness, but the top is flux. So you see there was 2 pointings per day. It was a fantastic project. It was 2 pointings per day for about 220, 230 days. And you can, each of them had a beautiful timing information and beautiful spectral information. It also had to have a large collecting area. These are power spectra, power density spectra of Cygnus X1 through history. You have Uhuru at the top left, which looks like random points. Then here 1 at the bottom left, you have some decent error bars. Exosat in the 80s had small error bars, and RXTE gave you power density spectra. In this case, they had error bars well within the points. You can see a zoom part there. And so fantastically flexible, all-scan monitor and large area was a perfect combination to start doing studies on galactic X-ray sources. And I will describe some the main results, what I think are the main outcomes of this mission. And the first one is the missing link. And that was a very exciting result. Briefly, we know a few days ago they announced they reached 400 radio millisecond pulsars discovered. And there was, and there is, of course, a very good idea of how pulsars evolve. And that's in the plot on the left. Pulsars start in the big clump of ordinary pulsars. They slow down because they are losing energy because of dynamo effect. We see them. Then they pass this graveyard line where they cannot be efficient anymore as pulsars. The magnetic field decays. And then if they are in binary systems, the accretion might rejuvenate the pulsar, accelerate it again. And then we go to the bottom left where you have very fast pulsars. On the X, you have rotating period. And on the Y, the magnetic field. You have low magnetic field, very fast pulsars in binary system, and we see them. The problem with this game is that we see the ordinary pulsars, we see the millisecond pulsars, we see low mass X-ray binaries accreting neutron stars, but we don't see pulsations from the neutrons. We didn't see pulsations for the neutron star. You have a sequence in the lifetime of a system like this. Here, the number 3 is when your pulsar is there already and is being accelerated by the companion accreting matter onto the neutron star. So where were these pulsations? These neutron stars had to pulsate fast. Why were they not pulsating? And this changed because of XTE when there was a small insignificant transient observed by Beppo Sachs in 1996, which appeared again in the sky in 1998. It was called Sachs J1808. And XTE detected pulsations at 2.49 milliseconds. You can see a power density spectrum there. You can see a clear peak, and it's obviously a very significant peak at 400 hertz. And also the pulsar was modulated at 2-hour period with a circular orbit. So we had exactly what we were waiting for, a system that's very fast pulsating, 400 hertz, 2.5 milliseconds, and it's a perfect progenitor for the radio neutron stars. Radio millisecond pulses. Now we know 15 systems, unless I missed some. They have rotations between 182 and 599 hertz. As far as I remember, all of them have been discovered by XTE. And because then we got wiser, we were looking for bright sources, and it turned out that the insignificant small transients were the best sources to look at. And then a lot of things can be done with these ones as well, because you can work on constraining the neutron star equation of state by modeling the pulse shape of these pulsars. It's quite a complicated thing. You can see on the right a mass radius plot for neutron stars and an area, which is what we can now put certain neutron stars in, and we can exclude some of the models. Also, the period distribution is okay. You see a period distribution in the histogram there. And it's compatible with the period distribution of the 400 millisecond radio pulsars that I was telling about before. Not only, we saw intermittent pulsations. You need very extensive observations. That's XTE, it's very flexible. Aquila X1, one of these neutron star systems, was observed for 361 hours during the lifetime of XTE, and only for 150 seconds, upper right, it did show pulsations. So it was, you had to look a lot to find pulsations from some of these systems. And even a new source in the bottom, Sachs J1748, showed pulsations, and they were in a, even the orbit could be recovered by the pulsations. So it was amazing that you had to observe for 361 hours, which is an enormous amount of time, just to catch 2.5 minutes of pulsation. And XTE, I didn't say that, but XTE was terminated possibly before the end of its active life in 2012. But work, of course, kept going on, and eventually people found even a better missing link: transitional systems, systems that were transitional between radio pulsar and accreting pulsar. First, they found systems that were in one state, and there was evidence that they were in the previous state. And then in 2013, a system was found that really was observed to do a transition from one to the other. So we really know what is going on. Now we have a final missing link. We know the evolution of neutron stars throughout their life. Second, high frequency oscillations. This is something that people are really looking forward to study with XTE. I'm talking about very fast oscillations from neutron stars. We know these systems, these accreting systems, extensively. We observed them before, and we saw that there were timing signals. This is the power density spectrum from the 80s, where you see a peak there that gives you a frequency. The frequency is very interesting. However, it's 1070 hertz. It's not fast enough to be something dynamically orbiting around the neutron star at very small distance. The phenomenology was very complex. There were complicated models being produced, but you want to see a really hot smoking gun of something that is orbiting a few kilometers from a neutron star. And then RXTE was launched, and very quickly, the first observations that were done to the brightest source in the sky, COX-1, showed something completely different. You can see the 4 plots on the right showed you peaks at hundreds of hertz, or a couple of peaks at hundreds of hertz. And these are really the signals that people were waiting for. The frequencies change. You can see the bottom left plot shows the 2 frequencies as a function of the hardness of the source for 2 peaks. So they move a lot from, say, 400 to 1200 hertz. They're not pulsations. They're not very sharp peaks, but they are decently sharp peaks. And they correlate with the low frequency cousins that were known before, and people were much less interested in at this time. Now, this was the first tool that we had to go very close to the surface of a neutron star, of an accreting neutron star. And for instance, if you identify one of these peaks as a Keplerian frequency, you can immediately put limits on the mass radius plot for neutron stars. The fastest one has been observed was 1220 hertz. You can see the line there. And that excludes all the shaded area there, simply because it has to orbit outside the neutron star, of course, because otherwise it couldn't orbit there. So you put, depending on the radius, just on Keplerian frequencies, you can put a limit on the equation instead of neutron stars. If you could see 1800 hertz, which we haven't so far, then we could constrain it even more. But then models started coming up, and as far as I know, all the models that have been proposed for these things rely on general relativity. And the first one was the relativistic precession model developed by Luigi Stella and Mario Vietri at the end of the 90s. That was a very simple model in the sense that it just identified features that you observe with relativistic frequencies: the orbital frequency, the periastron precession frequency of an orbit, and the length steering frame dragging frequency of the same orbit. So if you have a certain spatial radius, you identify 3 frequencies. That's very simple. There's no accretion in this. And it didn't work perfectly, but it worked surprisingly well. You can see on the right plot side, the low frequency versus high frequency. You have 3 peaks, 2 high peaks and 1 low peak. And the model was expected from the model was a square relation, and it works pretty well. Not perfectly, but pretty well. And then it predicted that the difference between the 2 high frequency peaks had to follow these curves depending on the mass of the neutron star, 1.82, 2.2. And it doesn't really. These are many systems, but the points are all there. So this plot, this model predicts that at low frequencies, they should be correlated, delta nu could be correlated with nu, and it is. It predicts that at high frequencies it should be anti-correlated. It is, although it's quite scattered and points don't really follow the line. And it predicts that you shouldn't have any above 400 hertz. And you don't have any above 400 hertz. This is the whole archive of XTE being put together in one plot. Then this model has been refined with accretion, at least for the low frequency part. I'm not sure if this is a movie running. Yeah, it's a movie running. You can put this into accretion physics by having two different flows in the accretion matter, and then have the inner one precessing at this length steering frequency. And then if you do this, you can actually predict more and connect that to the spectral models that have two different parts of the accretion flow. And things seem to work very well, but now we're reaching the limit of the data that we have. And also, I've been talking about neutron stars. Of course, you might wonder what happens with black holes. Black holes are not that clean. They should be cleaner, but we don't see many. There's a plot here, which I made myself with the data from Morgan, Remillard, and Grein in 1997, the first high frequency oscillation observed in black holes. That's about 70 hertz, 65 hertz. But it's very weak. It's there very few times, very few systems have been observed with these peaks. There are lower frequencies than the previous ones, which is good because black holes are heavier. And they seem to be mutually exclusive with the low frequency ones. So it's quite difficult to connect them. One source had 51 detections, but we'll see that better later. And if you apply the same model with the three frequencies, you need to have three frequencies. And in 16 years, millions of seconds, there's only one observation of one object that shows all three peaks, or it shows three peaks. And that's the one in the plot on the upper right. You have three frequencies to play with. And if you use these three frequencies and you put them into the model, then you get a solution that gives you the radius at which this oscillation takes place, the mass of the black hole, and the spin of the black hole. And you see the box there. The mass was 5.31 solar masses, and the mass known for the object is 5.4. So it actually was quite precise, but we only have one, even in 16 years of XTE, and we need more. We cannot really do it now. Then there are correlations between frequencies. I don't want to talk too much about these things because they are just too complicated, but all these frequencies correlate, and apparently this model can also address some of the correlations between these frequencies. And this works even in the case of the source that we were talking about before, but this is far too much. Then we have explosions and oscillations. There was another major result coming from RXTE. We know in the upper right, you see a time series of an object that has eclipses, you can clearly see, and has big peaks. These big peaks are called X-ray bursts, and they are episodes of nuclear burning on the surface of the neutron star. Matter accumulates on the surface of the neutron star, and then nuclear explosion can start. We know them since a long time. We have 115 systems now. They're a signature for neutron stars. Black holes cannot do this. If you see this, you have a neutron star in your hands. They can be used as distance indicators. If they reach the maximum Eddington luminosity, then you can have a kind of standard candle. You can see, well, this is not particularly important, but if you look at the gray plot here, you see the difference between the PCA energy coverage and the one of the current instrument NICER, which is much softer. And these are the spectra that you see or you expect. So in this respect, this new instrument is actually better than PCA. But at the time we didn't have it. And what was observed was that during some of these X-ray bursts, there were oscillations. These two plots are just two examples. One of them is a bit out of focus. You have time on the x-axis, and on the y-axis you have the little plot is the burst, so it counts. And then the contours are the frequency at which a peak is observed. And you see this peak, in the big one, you have a peak that starts at 329 hertz and evolves, and then in a few seconds reaches 330.5 or something. In the other one, which is our old source, SAX J1808, you have a very precise 401 hertz frequency, which is the same frequency as a neutron star. So you actually can see the rotation of the neutron star during one of these explosions. And it turns out many sources only have this as a pulsation. So if you see one of these, you know that, for instance, the one on the right is spinning at 330.5 hertz. If you look at it 2 years later, you have another explosion and you will see the same frequency. So this should be the frequency of the neutron star. And then it was proven because Sachs J1808, as I showed there, had one of these, and it's a 401 hertz, which, if you remember, is the same rotation of the neutron star. And this gives an even better instrument or tool to study the neutron star, because now we have something that it burns on the surface of the neutron star. It will start from a certain location. It cannot start everywhere on the star. It will start spreading, and then you have to model this spreading. This is not an easy thing to do. These are two models here because at some point you have you should burn the whole star. And if the whole star burns, then you're not going to see any hotspot rotating. You don't see any periodicity. So you still see the periodicity, then it has to either stop or it has to have some large-scale waves that replace the hotspot. But in either way, if you model the oscillation during the bursts, which is something very complicated that I never attempted doing, there are people who are doing it much better than me, then you can actually put, again, constraints on the neutron star equation of state. And you can see that in a plot, the areas that you can start reaching with RXTE. That's the dashed one. If you want to really go well, you have to go with a new instrument, but I'll talk about it a bit later. Then we have transient X-ray binaries. Again, here we had so much coverage that if you look at this color plot, the plot doesn't say much. It just flux versus time of all the black hole binaries observed for 5,000 days with XTE. And you can see just the density of points is amazing. Before the launch of XTE, or just about the launch of XTE, there was a major review published on black hole binaries by Tanaka and Lewin. And that review, if you go back to it, described for each source we knew all observations ever made. It's amazing because they could do it. Now, if you want to do something like this, you have to write an encyclopedia. If you write a review, you have to select what you want to say. And then what we found out is that the plot on the right, even if you do it for one source, doesn't tell you much. What you have to do is plot the flux of the source versus its hardness, an idea of how hard the spectrum is. And if you do it, you see it on the bottom right, the top plot, you see this Q-shaped diagram, which repeats quite well. While if you look at the bottom plot, you have three light curves. They are completely different. It's the same object having different outbursts. So they look completely different if you look in time, but if you look in this plot, they don't. And we made a little movie some years ago where you can see the evolution of one of these objects. This movie is 1 second is 1 week, and each dot is an observation. And this is of course the best behaved source, but it was possible to follow all these things in detail. And now we know how these evolutions go, which is very important. If you point an instrument like Chandra or XMM or something that you can only observe once or twice per period, then you have to know where you are in this diagram or where you want to be in this diagram to trigger your observation in order to do the study that you want to do. This plot that by itself doesn't tell you anything, but you can use it to do more observations or to select some observations. And then from this plot, we can extract a lot of information, not from the plot, but based on this plot. And for instance, for spectra, we have hard spectra on the right, as we knew, of course, and we have very soft spectra on the left, where different parts of the accretion flow take over the emission. And then you have a continuous variation in the middle. The plot at the top is mirrored in X because it was in time, and time goes from right to left. And you can see a temperature, you don't see it, but it's a high energy temperature. The accreting flow cools from 110 kV down all the way to 60 kV, and then it becomes hotter again, or something changes again when there are the big transitions. As timing goes, then you have very different things here that I'm not going to describe. You have a lot of variability on the right side, almost no variability on the left side, and you have beautiful peaks, which are the QPOs that I talked about before, in the middle. And this diagram has been extended to neutron star sources on the left, and even there's been an attempt, or there's been attempts to put AGN on the same graph, although this is a very complicated thing. And also the properties of emission of relativistic jets, which of course are not observed with XTE, are related to the position on this diagram, and even the presence of winds in these disks are related to the position in this diagram. So if you look at this diagram, you know what you can expect and where you have to look to go and look for certain characteristics. As I said, not all sources behave like this. Fortunately and unfortunately, some of them are a bit bizarre. They don't really follow fantastically this pattern, but most of them do. However, there is one source that does not follow it at all. And we've seen it before. It's a very peculiar system called GRS 1915+105. It was discovered in 1992, way before XTE. And in 1994, Mirabel and Rodriguez showed superluminal radio emission, two lobes moving seemingly faster than light from this object. It appeared in 1992, and it's still with us today. It hasn't disappeared, although it has become a bit weak lately. Now, this has been observed for, I don't know how many times, it's like 5 million seconds or something like this. And the reason is not really this radio plot and superluminal ejection. It's because the variability is unbelievable. And these are just 6 cases which I quickly plotted yesterday for this presentation of 6 selected series of about 1 hour, I think, or each of them is 1 hour of this system. And you can see what I'm talking about. These 6 plots are completely different from each other, and huge variability, and it has a very precise shape. And this shape changes, but not that much. There are 12, 13 different types of these things, and they keep repeating. You look at it now, 20 years later, and you see the same things. You even see some like the bottom right, which is the closest thing I've seen to interstellar communication. It's a sequence of digits. You can see these dips going clumps, 1, 2, 3, or 4. So you can actually extract a sequence of numbers. And if you want, you can check if it's pi in some particular base. Now, this has been the source of fantastic results of all types, because not only finding out why it varies like this, and we don't know, now we have another source doing this, but it's because the variability itself can give you great results on accretion in general. And so it can actually help understanding other sources, even if you don't know exactly why the shapes are so complicated and you don't know how to reproduce them. And also, as I said before, this was the only object that had quite a few high frequency oscillations. The right plot is the one I showed before. That was a fantastic discovery, and you can see the peak very clearly even in the main PDS there. And on the left, you see the distribution of frequencies discovered with XTE, and they're all about 65 to 70 hertz. It's a very precise number. This source has a very precise frequency, which is about 70 hertz. It's not incredibly precise, but it's always the same, more or less. And what can it be? We don't know, because the only fixed frequencies you expect is the one when the disk is at the innermost stable circular orbit. So that's a hard number. So if you have, for instance, a Keplerian frequency at that radius, it's a very precise number that can repeat itself. Unfortunately, it cannot be that, because we know the mass of this object, and even in the best case, it cannot be so slow. Minimum could be 90 hertz. So if you have 70 hertz, it has to be something else. And this thing has been seen even after XTE, fortunately, and it's again at the same frequency. So this is something that still has to be understood. And thanks to XTE observations, we also had a very clear connection for the first time of all this variability, and radio emission. You see on the right plot, a very famous plot of one of these X-ray light curves, and then there are two radio curves. On top, you see radio flares or radio high emission that follows events in the X-rays. And you can see in the left plot, it takes a while to see it, but the top is radio, and radio clearly is kind of sinusoidal there. And then in the middle plot, you have the X-rays, and every time you have one of these big dips, it is followed by one of these big peaks in the radio. Of course, you only have 4 dips visible in the X-rays, so it's not that easy, but there are other cases where you can pinpoint that better. So we know that was the first time that we saw exactly something happening in the X-rays where matter is accreting onto the object, followed by something leaving the system as observed in the radio or in the infrared. And now this is done on different systems, but here you could do it on very short timescales. Unfortunately, not on incredibly short timescales, but it is still a fantastic object. If it starts doing this thing again, then we can continue having new observations and discover new things about this relation between matter that is just about to fall into the black hole and suddenly decides that it wants to escape it. And then this was a very, very unique event. I call it a thrice in a lifetime event because we only know 3 of these things. In 2004, there was a giant flare from a neutron star, from a magnetar called SGR 1806-20. It was 27th of December 2004, and this event was so strong. It was, I think, was the strongest thing observed on Earth since the Kepler supernova a few hundred years ago. It disturbed the ionosphere and communications, and it was observed by all satellites, whether they wanted or not, because it was so powerful. It just went through wherever, whichever pointing you were having, you were getting X-ray photons. Only 3 of these events have ever been seen from 3 different objects, and fortunately, it took place not one day before, but one day after the big South Asia earthquake and tsunami, because otherwise people would have claimed that the giant flare had caused the tsunami, while it's more difficult to claim the opposite. As I said, as I wrote there, it's seen, not observed. XTE was observing a cluster of galaxies while it was invested by all these photons, and this is the light curve that you could get. The spectrum was completely distorted because you had a lot of brainstorming photons from photons hitting the instrument, hitting the walls of the instrument. But you see a precursor, and then you see a fantastic peak. This is a log scale. If I had done it in a Lin scale, this peak would be completely off the scale. And then you see this kind of jumping lion shape with a clear periodicity. That's the periodicity of the source. It released 10 to the 46 ergs in 0.1 seconds. Why do I say this? A lot of instruments saw this. The problem is that if you have XMM, XMM has very nice mirrors, but if the source is not on axis, then the mirrors are useless, and what you're left with is a kind of a small instrument on the focal plane. XTE was PCA was proportional counter, so even photons coming from the side would give you a lot of area, and that's why we had so many counts. And what was found was oscillations. The first one was very clear, very obvious. It's a 93 Hertz oscillation observed with RXTE. Only in a certain part of this outburst. You see it in the rightmost plot. You see this little black island in frequency at about 93 Hertz. And then people looked and observed 18 Hertz, 30 Hertz. I think those came from XTE, 150. I don't know where it came from. And Rossi, a solar mission, found a 1,840 Hertz signal from this neutron star. And this is very interesting because there are clearly oscillation modes on neutron star. The neutron star was hit by this explosion that is due to something else, but then it will have oscillation modes. And at the beginning, we thought that the 93 Hertz could be the oscillation mode of the 2 halves of the orange oscillating in the wrong direction. It's very difficult to do if you don't see what I'm doing. But then it turned out there are so many oscillations, it's actually pretty difficult. We just noticed that this oscillation was actually seen and detected even in the earthquake of the day before in South Asia. So this is something that, of course, you need to be lucky and observe. We haven't seen any since 2004, and obviously there are not that many. It has been calculated that if this thing had been too close to Earth, it would have completely wiped out life on the planet. So these are dangerous events. You don't want to have too many. So these were just some of the results, the main results, some of the main results obtained by RXTE. There are many others. But then RXTE in 2012 was terminated. It was switched off. And so we didn't have this anymore. And for a while, we didn't have anything that was even comparable to this for this kind of studies. Now we have some current instruments. And in particular, I think we have two. One of them is the Indian satellite AstroSat that I'm partly involved with. It was launched in 2005, and it had different instruments. It has different instruments. It's still working. But the important one here is the 3 large proportional counters called LUX-PC. There's a picture of one of the modules that I took myself at some point in India. And the graph shows the effective area of this instrument. That's the light gray one, the big one, compared to the XTE one, which is the middle gray one. And you can see it's the same below 10 kV, but it's much higher above 10 kV. This was obtained by having a higher pressure in the proportional counter. And actually XTE at the end of its mission had only 2 instruments working, and that's the dark gray area. So this was a very nice improvement, considering that the variability, the intensity of variability goes as the points for low frequency and high frequency peaks. So they are stronger at high energy. And if you don't have this drop in area, then you can see things better. And so it worked pretty well with a very different strategy of observation. It was not as flexible, it is not as flexible as XTE. You cannot point it at will like XTE was. I remember once I was at Marshall in the US, and I wanted to trigger one of my observations with XTE. It wasn't very important in the sense that there could be a trigger next week. It was not very rare. But I decided to send an email to James Funk saying, if you have nothing better to do, then you might consider doing my observation. And I immediately got a reply saying, we are slewing to it. That's how flexible it was. I just sort of imagined someone with a joystick repointing the satellite. AstroSat was not like that. It is not like that. Yes, I'm still stuck in the past. But it has a different strategy that is complementary. You can see in the left plot, you see an observation of one of the current, of the recent transients, and that's 5 days of pointings, one after the other. And that was not easily done with XTE, and it is not done in the same way with NICER right now. And so it's that 5 days completely dedicated to our source. And you can see here the evolution of a low frequency oscillation as a function of time. NICER, which I will show in a moment, also observed this source, also kind of saw what we saw here, but it was buried in the whole set of observations, and we found it much better with this one. And as I said, this high frequency oscillation of GRS 1915 was observed again with AstroSat. And for the first time, we managed to see, that's the right plot, changes in the frequency correlated with the spectrum. So when the spectrum is harder, the frequency is slightly higher. And this is, of course, this is not terribly much better than XTE, because the instrument is not really a big jump from the PCA. We need something much bigger in order to show something much better. This is a kind of same quality of data. It was a very good observation, and this thing could be seen. XTE did not see that. And then there's another instrument, which is NICER. It's a neutron star interior composition explorer. That's not a satellite. It's an instrument put on a space station. You can see, I'm not sure, I think it's a real picture there. It's a NASA instrument launched in 2017, and it consists of 56 concentrators with SDD detectors. It doesn't do imaging, again, and it's aimed obviously at neutron star interior composition, at observations, spectral and timing observations of neutron stars, but it can also observe black holes. The effective area is compared to the XMM Newton one here, not to the XTE, but it's 1900 square centimeters of 1.5 keV, and it has a softer response than XTE, which of course is not good for certain things, but it opens a different window on others. And it's also very flexible itself, which is a very nice, fresh wind from the past. And you can see here, that's a result I had, where you could do, if you look at the right plot, the delay between hard and soft photons that's the bottom right plot in one of these transients. And XTE basically observed only after the dashed line, which is a reference band. And so it had only hard photons delaying soft photons and going down to very small delays. Now we could observe below 3 keV. And what you see is that these legs go up again. So this is something that clearly was not possible to do with XTE. But of course, these are very good instruments, but we are looking to the future. We're looking forward to new things. It's not that easy to have one of these big timing things accepted. It has been tried quite a few times, but now I think we are in a good direction. And we have EXTP in the future. It's a collaboration between China and Europe. It has 4 instruments, you can see in this plot, and one has the large area. The 4 instruments are a wide field monitor. As we know, it is important to observe the wide field instrument to catch things. Then you have concentrators. The PFA, SFA are telescopes. P is for polarization, and then the other ones are just for flux and spectral measurements. But then the big instruments is the LAD. That's the one that looks like solar panels, the black ones. In the previous versions, they even look like bigger than solar panels. It's 3.4 meters at 8 keV, which is way more than we had before. You can see the effective area there on the plot there. The LAD, the large area detector, is the red one, and the XTPCA is the blue one. And now the difference between AstroSat and XTE, you can see it at the bottom, becomes a small ripple in the area compared to the area of XTP. And it's, of course, it's not a large area proportional counters, because you cannot really launch a swimming pool of gas in orbit. It's more modern silicon drift detectors. And it has a 230 kV resolution coverage and a good energy resolution, which XTE did not have. This is something in the future. It's possibly going to be launched in 2027. And here I have, from the white papers that have been published, some of the predictions. You can see the bottom left, you have, you've seen this plot again. It's the expected area on the mass radius for neutron stars that would really constrain the equation of state of neutron stars. Then on the upper left, you have the emission, iron emission line from GRS 1915 as a function of the oscillation. So you can do fantastic spectra on a very short time scale as you resolve the quasi-periodic oscillation. And then in the big plot, you see a time frequency image of high frequency and low frequency oscillations changing in time with a very high precision. And then if you want to follow your favorite model, like the RPM, if it followed the RPM, you would expect the red line, and the red line, of course, here is followed perfectly with very small error. So once we have this, there's really going to be a change that, of course, builds on RXTE. We know what to look for. We know when to look, which was not obvious before. So if you only have one shot at one source, I can tell you when to look. You don't have to spend 2 years looking every day. There's just a good period where you can find certain things. And then there is something which I think is still at the concept study. It's not expected yet to be hardware. STROBE-X is a similar project on the US side of the Atlantic. 3 instruments, one with a large area, which is actually called LAD, like the other one, 5 square meters at 10 keV, a wide field monitor. You can see the area again in the plot there. So we're talking about something similar, but with I think a higher coverage at high energies. And again, the plot at the top I put there, but I have no idea exactly what it means. But the bottom one, you know, because you've seen many of these, it's a mass radius plot of neutron stars. And you can see again with an instrument like this. With XTE, you can only have a very large area allowed in this diagram. And with the STROBE-X instruments, you will have very small areas. If you do more than one observation of different objects, of course, then you can have different points and really follow one of these lines. And this was my last slide, and thank you.
Thank you, dear Tomaso. I think it was a beautiful review to show how the timing, the view of the timing in our universe changed, getting closer to the neutron stars with burst oscillations, to tracking the whole black hole cycles in timing and what we can observe and learn, even having unexpected observations, which was, I guess, this giant flare from a magnetar. I think it's a beautiful overview how important RXTE was and how he changed actually the view of how we are observing or how close we can go to neutron star or black holes or compact objects. At this point, I know you are very deeply involved in the RXTE data, but when we have a mission, we have also to say always thank you to the people who actually built the mission, to all the engineers and the PI and the scientists that oversee in the US, in the NASA, who built such a beautiful instrument as a game changer. So well, Tomaso, thank you.
And they run it in a fantastic way.
Of course, they build it and they run it, of course.
Many people built beautiful instruments, but the way it was designed to run, and it was run, was really unbelievable. It's we are not going to have something like that. Even Swift, to a certain extent, is not the same thing. Although it can point.
That's true. You have also great things from Arvin Palmer. And so to all the attendees, you can raise your hand to ask questions or to write your questions in the chat. I think we have already one question, or let me read it. You were right to highlight the flexibility of RXTE. It was really crucial and designed that way together with a superb project scientist, Jean Zwanck, which was, it's still the comment from Arvin Palmer. And yes, indeed, we are thankful to all the project scientists of RXTE. We have one raised hand, which is Didier Barret. Please, Didier.
Oh, wine.
Can you hear me?
Yes.
Hi, Tomaso.
Hi,
I'm Mauricio. Yeah, in the list of, it's a comment, in the list of missions which will have some timing capability, I will not forget Athena, because it's due to be launched in the early 30s. And in particular, as you know, we are pushing as hard as we can to bring timing and high spectral resolution together with the XIFU. And this is possible because the mirror will enable defocusing, and with the combination of very fast microcalorimeters and the combination of a filter, beryllium filter on the filter wheel, we will be able to observe hopefully sources as bright as one crab with the, say a few eV spectral resolution. So I would not want to forget that one, because this is driving the XIFU, and there I expect also some opening a new discovery space. That was my only comment, but thanks for the presentation. It was all beautiful.
I didn't want to deny it. It's just that the ones that I showed are can be considered to be hairs of XTE, while Athena is something. It's a different type of project. So these ones were the same thing but bigger, so to say. So in that direction, while Athena is something that has other capabilities. Although of course EXTP has other capabilities as well. It has the polarization, but I just limited to these 2 or 1.5 because STROBE-X is not yet a mission. But you're right, of course. Yes, indeed.
Thank you for the presentation. Very nice, Tomaso.
Now, I have, please ask questions. And there are also some nostalgic comments. It was from Tiziana Di Salvo and Luciano when it was a beautiful time when you could discover a QPO just opening your computer. So I hope we can still do this in the future too.
You know that one thing that was possible only for the first part of the mission was to connect to a special screen and see your data arriving in real time. You would see your light curve building in real time on your screen. It was not particularly good for QPOs because you don't see a QPO in a 1 second light curve, but you could actually have X-ray glasses and look at the sky, and I saw an X-ray burst live in front of my eyes in the building in the light curve. So that was quite exciting. Then they stopped it because it wasn't really particularly useful. So
Okay.
Probably was expensive.
Let's see, there is another question. Can you please explain how high pressure XE gas in AstroSat and LAXPC provide broadband energy coverage than RXTE PCA?
Well,
So
I think I'm not an instrument person.
Yeah,
I break
more engineering.
But, if you have a higher pressure, then you can capture higher energy photons, simply. So you extend your high energy end of your response, of your linear area of response. Then the drawback, of course, is that now you have to keep a 2-atmosphere box of gas in space. And that's more difficult, challenging than having a 1-atmosphere tank of gas in space.
So one more question from Eric Kulkers. Did RXTE also discover QPO from AGN?
That is a question.
That's a question, yeah. If RXTE also discovered QPOs from AGN.
No, I don't believe it.
Okay.
I think that the big one, the RE something was XMM.
Mm-hmm.
And I don't really believe other detections. Okay. What I didn't say, because it wasn't really a big game changer, but XTE was clearly aimed at galactic sources. Unfortunately or fortunately, galactic sources are in the galaxy, meaning that they are actually mostly in the same place in the sky, in the galactic bulge. Therefore, you cannot observe the same area of the sky 100% of the time. And they observed a lot of AGN during the lifetime. They had monitoring programs for 16 years. Just to, even if you didn't want to, you had to, because you had to cover the certain areas. And that provided fantastic long-term light curves of AGN. Mm-hmm. So that was really beautiful work. And I think about half of the time of XTE went into AGN.
Now I have a question to you, because before you told that we are lucky that this giant flares doesn't happen too close to our Earth, but how close are the closest neutron star to have such, or magnetars, I have to say, to have such a giant flare which would actually destroy, let's say, our
no idea.
Our life on Earth.
Well, there is an old rule that I tell my students: if you have something rare, it's unlikely to be near home. And so the magnetars are not, I don't think, are very common systems in the galaxy. And so it's unlikely that you have one near your house. Not impossible, of course. I don't hear you anymore.
Sorry.
Maurizio.
Yes, sorry. We have one more question, and then I would like to stop here our online seminar. It's the last question. It's from Tiziana Di Salvo, and the question is: since all neutron stars are rotating, and since some anisotropy in the emission from the surface is expected at some level, for example, magnetic funneling, etc., in perspective, giving an instrument, so we're giving an instrument of sufficient area, it is conceivable that we could detect the rotation of all accreting neutron stars, making a quantum leap in our understanding of neutron star equation of states. Do you agree on this?
So if we have a big enough instrument, we should see them all. I'm not sure. I think it's still unclear why we don't see the main ones, like the main no mass X-ray binaries are never been seen observing and pulsating. And still people don't know. There are different ideas of why this is the case. And so I don't know if we can see them all or how big the instrument should be to see them all. Really.
Mm-hmm.
It would be sufficient to see many more, and then we'd have a lot of answers.
Yeah, there is one thing I would like to mention, which I think it's quite important from Gottfried Kahnbach. I mean, yes, it's true that, you know, in all these X-ray missions, and not only, I mean, the multi-wavelength observations, it's always critical to understand actually what we are observing. And I mean, also one plot was, one of your plot was with X-ray and then radio data together. And of course, you can extend this to brighter and multi-wavelength observations, which is indeed crucial for all missions, I guess. And I will stop here to say thank you once more, dear Tomaso, for having accepting to give this beautiful talk. And let's keep crossing our fingers to see more timing missions flying and providing us with new data and insights to make one step further in our understanding of the violent universe or on the compact object. So thank you to all the attendees. Thank you, Tomaso, once more, and have a nice evening.
Thanks. Goodbye, everyone.
Bye.